In the final part of Chapter 6, we're going to study two quadrilaterals. So they're four-sided figures, both of them. But they don't quite make it into the parallelogram family, which is what we focused on for most of Chapter 6. Remember, parallelograms are a rhombus is a parallelogram, a rectangle is a parallelogram, and a square. They're very, very specific types of parallelograms. But just to be a parallelogram, you have to have one characteristic would be both pairs of opposite sides are parallel. So what we start to see with the trapezoid is that we have one pair of opposite sides that are parallel. Okay, and if you remember, in a parallelogram, we could have one pair of sides that was parallel and congruent, and then that would make a parallelogram. But you can see this side up here is parallel to this side, but they're not congruent, so it's not going to be a parallelogram. And we had also pointed out that if we had one pair that was parallel, like this pair here, and then another pair that's congruent, appears to be here, that's still not enough. They would have to be both from the same pair of sides. Otherwise, you could end up with what we call here an isosceles trapezoid. So the trapezoid is the first figure we're going to look at, and I'll explain the kite and how that falls short of parallelogram characteristics. But the trapezoid has just one pair of opposite sides that are parallel, and we call them the bases. Okay, the other two sides that are over here that are obviously not parallel, they eventually intersect, we call those the legs. And if the legs are equal, then we have what we're going to call an isosceles trapezoid, very much like an isosceles triangle. The legs are equal in an isosceles triangle and the base angles are equal. And the same will be true if we have an isosceles trapezoid, which is what we have here. We can see off to the side that we're showing that those legs are equal. That means that these base angles will be equal as well, and then also these base angles, okay, will be equal. They're not all equal to each other. These are consecutive interior angles, so they'll add up to 180. That rule will still be in play. So here we have an isosceles trapezoid. We can see that it's marked here. They want us to find the measure of angle D. So let's think about how we would find the measure of angle D. Since this is isosceles, I can move over here and get angle B right away. It's 125 degrees. I know that those two are equal. But the measure of angle D does not equal 125. These are consecutive interior angles off of parallel lines, right? Remember when we cross parallel lines with a transversal and we have consecutive interior angles, they are supplementary. They're going to add up to 180. So in this case, in order to find the measure of angle D, we want to take 180 and subtract 125 from it. Okay, so the measure of angle D would be 55 degrees. And in the next example, I'm going to once again infer that I have an isosceles trapezoid. They don't mark that the legs are equal. They mark that the base sides are parallel. I can see parallel markings here, so I know the bases are parallel. I know the legs are congruent because they're both labeled as lengths of 5. So that makes this an isosceles trapezoid, which means this is 40 degrees here. But they want angle L. So angle L, just like we did previously, to find the measure of angle L, we would take 180 and subtract away the 40 that lives right next to it. So the measure of angle L would be 140 degrees. So I have two layers to these examples. I want to first and foremost decide whether or not I have a trapezoid. Okay, so in order to have a trapezoid, we'll need two sides that are parallel. And then if it's isosceles, the legs are going to have to be equal. So we're going to use really two formulas here, potentially the slope formula to see if the sides are parallel, and then the distance formula to see if they're congruent. Okay, so these are the points that they've given me here, A, B, C, and D. I've plotted them. You can double check my coordinates there, make sure that I put everything in the right place. But everything looks good as far as I can see to troubleshoot here. So the first thing we're going to do is let's think about the sides that look like they might be parallel. AD and BC. What is the slope of AD? As I move from one point on the other from A to D, I go up 2 and over 1. So the slope of that line is 2. And then from B to C, we go up 1, 2, 3, 4, and over 1, 2. So the slope of BC is, we go up 4 and over 2. That's also a slope of 2. Okay, so this is a trapezoid because AD and BC are parallel. Now, I can really just tell by looking at this, it's not isosceles. In order for it to be an isosceles trapezoid, this segment here would have to be equal in length to this segment here. And I can very well tell, even without using the Pythagorean theorem, which is what I would use for my distance formula, I have a leg of 1, and then 1, 2, 3, 4. So AB's length would be 1 squared plus 4 squared, and we would take the square root of that. For CD's length, we can see very easily that's not going to be equal because this is a length of 1, 2, 3, and up 1. So this would be 1 squared plus 3 squared, and we would take the square root of that, and we can tell right away those won't be equal to each other. So it's not an isosceles trapezoid, but it is a trapezoid. So in the next one, let's think about the sides that appear to be the bases here. JK, to move from J to K, our slope is, we go down 1, 2, and over 1, 2. So that's a slope of -1. We go down 2 and over 2, that would be a slope of -1. The slope of ML, as we move from one point to the next there, we go down 1, 2, 3, 4, 5, and then we go over 1, 2, 3, 4, 5. So the slope of ML is down 5 and over 5. -5 over 5 would also be a slope of -1. So we know that this is a trapezoid, okay? And then finally, let's look at the length of MJ. That would be one base. It has a length of 1, 2, 3. And then I look over here at KL, and that has a length of 1, 2, 3 as well. So what that means is that JKLM is an isosceles trapezoid. And I list my reasoning for it. Not only do I have parallel bases, which I can mark here, but I also have 2 congruent legs. So that's going to be an isosceles trapezoid. Okay, so in our last example here, when we connect the midpoints of the legs of a trapezoid, and notice I'm just marking that they're equal to each other, they tell me that M and N are the midpoints. When I do that, I create what's called the midsegment. So if HJ is 32, if that length is 32, and LK is 60, okay, the length of MN, which is the midsegment, is just halfway between the two of those. So we take 32 plus 60, we add those two together and divide by 2, and that would be our length of MN. So we have MN is 92 divided by 2, which is 46. And it should make sense there, right? To get from 32 to 46, I would add 14, and then I'd add another 14 to get to 60. Okay, so let's think about the next one. Here they give me a little bit different information. We still have our situation where we have a midsegment, but this time they tell me that HJ is 18, and they tell me that MN is 28. We have to find LK. So we could formulate an algebra equation here, or we could just use common sense, right? How do I get from 18 to 28? I added 10. So what I want to do to get to the length of this segment is add another 10, and it ought to be 38. And then we can check our work and see if this is correct. If I take 38 plus 18 and divide by 2, do I get 28? Okay, that's what I should get when I add those two together. So when I add these two together, I get 56 divided by 2, and that is indeed 28. So the missing side that they're looking for here, LK, would be 38 in this situation. Right? It has to be halfway in between the smaller base and then the larger base. And the second quadrilateral we want to look at here that sort of has some properties in common with some of the parallelograms we studied is the kite. So the kite has some sides that are equal, but notice they're consecutive sides. So MN and NP are equal to each other, but in the parallelograms they're supposed to be opposite. But what happens in this situation when we create a kite is that we get some rhombus characteristics. We have a 90-degree angle that's formed here in the center. The diagonals are going to be perpendicular to each other. Okay, and it's also going to have exactly one pair of opposite angles that are equal to each other, and it's usually pretty easy to see which angles are equal to each other because they're the ones that are going to be opposite, on the even side here. Like if I have 80 and 60 here, I can see these segments here are much longer than these. So the opposite angles that are going to be equal in this situation are going to be X and Z. Okay, so that's how it comes close to resembling some of our parallelograms. We have one pair of opposite angles that happen to be congruent, and we have the diagonals bisecting each other. Okay, so here we have some kites with some given measures and then some unknown measures, and I just repeated the pictures every time so that we can continue to draw on them for the next example. So In the first part here, I want to find the measure of angle J to R to K, and they don't give me any information, so hopefully this is a right angle, and it is. That's going to be 90 degrees, right? The diagonals are perpendicular to each other in all kites, so we can find that relatively easily. Now we have some information here, and I'm going to use the sketch next to the kite that I just drew on. RJ is 3, and then from R to K is 10, and they want us to find JK, this side here. So remember what we have here. We have a right triangle. So this is a Pythagorean theorem situation. I have the two legs of the right triangle coming off that 90-degree angle. So to find JK, we use our Pythagorean theorem. We have 3 squared plus 10 squared, and then we just take the square root of that. So this is 9 plus 100, still living under the radical. So this would be 109 under the radical, and you can just leave your answer as a square root situation there. Okay, now they tell us that GHJ is 90. That's not something we would be able to infer. They just let us know that that's 90 degrees. Okay, and then they tell us that the measure of angle G to K to J, if I move from G to K to J, that's this whole angle down here at the bottom, is 110 degrees. And they tell me G, KJ, 110. Doesn't make a lot of sense because it definitely doesn't look like it's 110 degrees. But now they want me to find HGK. Right? So where's H to G to K? It's this angle here. Remember, these two angles are opposite each other. They equal each other. And all the angles add up to 360. So if I take 360 and I subtract away the two angles that I have, the 90 and the 110, okay, what I'm left with is 160. But that's 160 for both of these angles. So these two angles would have to be 80 each. So if you think about the four angles that you have here, 110 plus 90 plus 80 plus 80 should give us the 360 degrees that we have in a parallelogram. So that means the measure of angle HGK would have to be 80 degrees. Okay, here they tell me that HJ is 7. Find HG, and remember HG is consecutive to that 7, so we know HG must be 7 as well. Okay. The consecutive sides are going to be equal to each other, just like these two sides here would be equal to each other. If HG is 7, as they tell us in the next one, and GR is 5, what would HR be? So we're going to lean on our Pythagorean theorem again, except this time we have the hypotenuse. So in other words, we know that 7 squared is actually equal to 5 squared plus the side that we're looking for here. We'll call that x squared. So in this situation, we'd have to subtract. So x squared would equal 7 squared minus 5 squared. And that would be 49 minus 25, which is 24. So that means HR would be the square root of 24. And we can just leave that under the radical, or you could rationalize it if you want to simplify that. We know that that breaks down into the square root of 4 times the square root of 6. So we could say HR equals 2 square root of 6. Either one of these is fine for our value of HR, or you plug it in your calculator and get a decimal. Okay, number 6, we have G to H to J is 52 degrees. So that's this angle up here. Okay. Then they tell me that G to K to J, angle living down here, this is similar to one that we already did. So that's this whole angle here. GKJ is 95. Find HGK. So I just want this whole angle. So this is really similar to what we did previously. We take our 360 degrees that lives in this kite to begin with. We subtract away 52, and we also subtract away 95. But we get 213. Remember, that's not our final answer. We have to take that 213 and divide it evenly into these two angles. They're the other two angles in the kite. We know they must be equal if these two opposite angles are not equal. Sorry, I keep hitting the mouse pad as I'm writing on my board here, and I get 106.5 degrees for each of those angles. So we get a little decimal here for the measure of angle H to G to K. It's going to be 106.5 degrees.